In this video, we're going to algebraically evaluate a function and solve an equation written with function notation. We'll then graph y equals f of x and look at the relationship between function values and points on a graph. So let's get started with the function that we have. We're given, let f of x equal 2x minus 5. So we're told how this function f is defined. F takes x and turns it into the expression 2x minus 5. So if we want to find f of 3, we are going to replace every instance of x with 3. So if we take f of 3, and I'll highlight 3 here with a different color. So f of 3 is equal to 2 times 3 minus 5. And we know that based on the relationship that f of x is defined with. So we're told that f of x equals 2x minus 5, so f of 3 is simply 2 times 3 minus 5. We can now simplify this, and according to the order of operations, we'll do 2 times 3 first. So we'll get 6 minus 5, which is then equal to 1. So what this tells us then is that f of 3 is equal to 1. Now quickly, this is something that we've seen before, and I want to compare it with evaluating a similar expression without function notation. So previously, we would have had something like y equals 2x minus 5, and then we'd be told that x equals 3. So when we go and evaluate this, we would get y equal to 2 times 3 minus 5, and that would be 6 minus 5, which is 1. And so this looks really similar, but the key distinction is here is that we are left with just y equals 1. And the key distinction between these two is that the first one, using function notation, allows us to retain that information of what the input value was. So the input was 3, the output is 1. We can see that in that equation, f of 3 equals 1. Without function notation, once we've evaluated, we're just left with the y value. So we just have y equals 1. And that's one of the key advantages of function notation, and we'll see how that ties then into graphing y equals f of x later. Next, let's look at solving f of x equals 9. Now, one of the things we want to note here is that we're given that f of x equals 9. We are not given the x value. We actually need to find the x value. So we need to note first that we need to find x here. We don't know what it is. And second, we're given an equation. And when we solve an equation, we are tasked with finding the value of the variable that makes that equation true. So we need to find the value of x that makes this equation true. Now, because we're given how this function is algebraically defined, we can simply go from f of x equals 9 to 2x minus 5 equals 9, because we know that f of x is 2x minus 5. So now we have 2x minus 5 equals 9. And this is a linear equation, so to solve it, we can add 5 to each side and find that 2x equals 14. And that will mean then that x is 7. So the solution to this equation, or the value of the variable that makes it true, is 7. So I'm going to write that here. The solution is 7. And if we were to state the solution set, we could say the solution set is, and then I'm going to write the set containing 7. So I'll just put the number 7 inside curly brackets. All right, now we're going to graph y equals f of x. And so to do that, we want to note that this is a linear function. And so noting that it's a linear function, we want to state then that its slope is 2, and we know that we're going to graph y equals 2x minus 5 when we graph y equals f of x. So the slope is 2. We know that based on the coefficient on x, and the y-intercept is the point 0, negative 5. All right, so coming over to our graph, let's scale and label these axes. And this is a 10 by 10 grid, so I'm just going to label with units of 1. So I'll mark off x and y to label those axes. And then when I scale them, I'll mark off 5 and 10 at 5 units and 10 units for each x and y. Okay, now I want to start with the y-intercept, and then I'll use the slope to find more points on this graph. So I'm going to plot the point 0, negative 5, and then a slope of 2 means that the rise over run is is 2 over 1. So I can simply go up 2 units, write 1 unit, and find the next point. And then I can do that again, up 2 units, write 1 unit, up 2 units, write 1 unit, and I'll just continue throughout this grid. I could also, from the point 0, -5, go down 2 units, left 1 unit. That'd be similar to -2 over -1, which is still equal to 2. And that would allow me to find more points in this third quadrant here. Now that I have a bunch of points, I'll connect them with a straight line. So I'll draw that through. And to show that it continues on for all real numbers, I will put arrows on the ends here. Okay, so I've graphed this function. Now there's a couple things that we should note. With regard to f of 3 equals 1, if we come over to this graph of y equals f of x, we can see the point 3, 1. So a couple notes that we want to note here is that the function value at 3 is 1. So the statement f of 3 equals 1, so the statement f of 3 equals 1 communicates that the point 3, 1 is on the graph of y equals f of x. But an even more critical point is that f of 3 is not the point 3, 1. F of 3 is simply a number. So f of 3 is not the point 3, 1. It's just a number. And that is a critical thing to note, is that f of 3 is the number 1. It's equal to the number 1. But that when we tie that to the graph, that communicates that when the input is 3, the output is 1. So in relationship to the graph of y equals f of x, we see that that corresponds to the point 3, 1.